Good evening, everybody, and welcome to tonight's edition of the Triangle Area SQL Server User Group's Advanced DBA meeting. We have the pleasure and honor of having Hugo Kornelis talk to us tonight about the 5 stages of grief, the internals of a hash spill. And this is Hugo's second go at TriPass this year, and we appreciate both of these sessions. So really looking forward to hearing what you've got. And in that case, please take it away.
Thank you, Kevin, and welcome everyone. Hi. This is a bit unusual for me. Normally I do this from home, but I am actually multitasking. I am in Mechelen in Belgium in a hotel room because I'm in the middle of a conference. I spent the entire day at the conference today. It's midnight now for me, and I'm here in a hotel room, completely unusual for me, presenting to you, and then tomorrow I will go back to the Belgium conference. So we are going to talk about the internals of a hash bill, and I've called the session 5 stages of grief. I'll get back to that in a minute, but first let me do a quick introduction of myself. My name is Hugo Kornelis, and I make SQLServerFast.com, which is a website I set up several years ago because I felt that we needed better documentation of execution plans. And that's what I started building, the execution plan reference, a completely free resource where I try to describe everything that's worth knowing about execution plans. Now, as a reference, it's not ideal for learning. There were people who asked me, especially after attending a pre-con I had on execution plans, and they said, you should make videos of this and put it online as a video course because it's very valuable stuff. And I thought, I can do one better. So instead of creating a video of my pre-con, I made even longer and more extensive videos where I explain everything about execution plans in the form of the execution plan video training. Now, there's so much time to invest to make that I decided not to give it away for free. Some of it is available for free as a teaser. The rest is for sale for, in my opinion, a very moderate price. But of course, even a moderate price is still too high for all of you. So I now offer you a 10% discount if you use the code FULL24 when buying access to my videos. This code is valid until the end of November. Or if you prefer to get 20% discount and no end date, then you can sign up for my pre-con at the PASS Summit next month in Seattle. And at the end of that pre-con, I will give a 20% discount code to all who are still alive, who survived my pre-con. Okay, that's a joke. I haven't killed that many people in reality. So on SQLServerFast.com, you will also find a link to my YouTube channel where I have recorded conference talks. I will probably link to this video later when Kevin sends me the link. And quick videos that I record based on conference talks. All that is available on SQLServerFast.com. I also have my blog there. I have articles. And very important, at the bottom of the screen, you see if you go to SQLServerFast.com and then use the menu to click other presentations and then presentation resources, you will see a long list of all my presentations. You can just click any of them, scroll down to where you will find a link to download a zip archive with both the slide deck and the demo code. For this talk, it's only the slide deck because this is a slides only talk. I will not do any demos today. I'm sorry for those who love demos. I love demos as well. But for this explanation, I really needed to visualize things. So I do a lot of other stuff. I do work. You don't care about that. I do, but you don't. The only thing you really care about is how to contact me. Now, if you have questions today during the talk, just type them in the chat. Kevin will relay those questions to me and I will try to answer them. If you have questions later, or if you watch this as a recording later, then you can always mail me or tweet me and I will try to get to your answers, to your questions and try to provide an answer. So let's get started. When I first had the idea to do a session on the internals of a hash bill, I had the idea and I thought it was kind of funny to liken it to the theory of 5 stages of grief, which is a theory for actual grief processing. So I created the name for the session, I created the abstract, and I started submitting the session. And once it was selected, um, I started building the session. And that's the point where I at first decided, let's make sure I get my facts right. Let's do some research into those 5 stages of grief. And then I found out something I didn't know. It's actually a contented theory. Not everyone agrees. And those that do believe in this theory of 5 stages of grief don't all have the same idea of what those stages are. So, yeah, there goes my idea of a fun session. Anyway, I decided to still keep it that way, and I used the most common theory that I found on Wikipedia. um, so if you go through grief processing according to that theory, you go to the 5 stages: denial, anger, bargaining, depression, and acceptance. Okay, we are not actually going to talk about this theory. The only thing I want to say is, if anyone in the audience actually struggles with grief at this time, please find someone to talk to, get help if you need help. There is always someone available for you. I know this session kind of puts it in a funny way, but I do want to make this very serious note. If you need someone to talk to, if you have nobody else, reach out to me. I will listen to you, I will let you talk, and I will look with you to see if we can find a way to help you. But today we are going to talk about the 5 stages of the grief of a hash pill, because a hash pill is bad for performance. We don't like bad performance, so we get sad, and then that spill can go through 5 stages: dynamic destaging in 2 phases, and then dynamic role reversal, bailout, and bit factor filtering. We'll go through all of them, explain exactly what happens internally. And for the record, you don't need any of this to work with SQL Server. It's interesting to know. It's nice, interesting background information, but you don't need it. The only thing you need to know is spills are bad, try to prevent them. But for those who are interested in, okay, but why exactly is a spill bad and how does SQL Server handle that? That's what I'm going to talk about. So to make sure we're all on the same starting point, I will start with a very quick refresher of how hash match works. And I'm going to use a hash match for join operations. Hash match can also be used for aggregation. There's a lot of similarities, some small differences. To keep it simple, I'm only going to talk about a hash match for join operations today. And that hash match runs in 2 or 3 phases. First, there's always the build phase, where the top input of the hash match is read, and all the data from that top input is stored in memory in a so-called hash table for easy retrieval during the next phase. Point here is that everything that is read from the build phase, all the input has to go in memory. Then the second phase is the probe phase. This is the phase where the second input is read, the probe input, and for every row from that probe input, the appropriate hash bucket is searched to find matches and return matches depending on the join type that is requested. And then again, depending on join type, for an inner join, it is not needed, for instance, but for a left outer join, this final phase is needed. We do a final phase to go through the data in the hash table to see if there's still any rows left that have no matches and whether we need to do something with them. So that is a hash match in very quick bird's eye overview. Now, because the build phase stores the entire data in memory, hash match requires a lot of memory. The optimizer decides how much based on cardinality estimates to determine how much memory it will needs to assign to the hash match operator to do its work. As of SQL Server 2017, there is a new feature, memory grant feedback, that can improve bad estimates on a second or third run, but the initial run doesn't benefit from that. And older versions didn't have memory grant feedback. So if you're still on SQL Server 2016 or older, or 2017 but running row mode, you don't have memory grant feedback, and you can really suffer from bad estimates. This memory grant is reserved before query execution starts. And that is important to be aware of. I'm actually currently at a client that had a big issue with memory grants where there were users complaining that they fired off a query and it took an hour before results came back. And I looked in the query store and it was like 5 minutes. And eventually I found out that that query had been waiting for 55 minutes before the memory grant was finally available. So you don't want the memory grant to be too high. But you also, I forgot about this. So the, oh yeah, sorry, brain fart. Forget I said that. So you don't want the memory grant to be too high, but you also don't want it to be too low, because once the memory is granted and the query runs, that's it. You don't get extras. You ask for 10 gigabytes, you get 10 gigabytes. So while running, you realize, oh, I should have asked for 15. Too bad, you asked for 10, you work with 10. So if HashMatch runs out of memory, Microsoft chose not to abort the execution plan, not to raise a runtime error, but to use tempdb as an overflow area to hold data that doesn't fit in memory. But the hash match algorithm can't work effectively on data in tempdb, so that means that also the algorithm changes at that point. And that's what we're going to talk about. So let's start with the first stage of a hash bill, the first stage of the grief of a hash bill, denial. Let's pretend there's nothing going on. So in the total process of dynamic destaging, we have several sub-steps. And the first that I mentioned is the in-memory hash join. And the in-memory hash join is basically doing la 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 la, can't hear you, I don't have a memory problem. Very optimistically, we are going to assume that everything fits. So this rectangle you now see on the screen, that is the available memory grant. In this rectangle, in this memory, we allocate a hash table, in this case a hash table of 9 buckets. Now, a real hash table will have thousands of hash buckets, but then you get such a tiny font on the screen and you can't see it, so I simplified it, but this is not a realistic example. We open the build input and we grab the first row from there. At this point, we apply the hash function to compute the hash. Let's say that this data hashes to the value 4. Then this row has to be stored in bucket 4. Now, the way SQL Server does this is through pointer change. So the data goes into memory somewhere and a pointer from the start of bucket 4 goes to this data. We need the next row from the build input. We compute the hash again, and this data goes into bucket 8. We need, then we read yet another row from the build input. We compute the hash, and hey, we have 4 again. That can happen. Maybe the same key, it may be a hash collision. Anyway, this data goes into bucket 4. So it's simply added to the pointer chain. And at this point, I do want to point out that in reality, the structure of the hash table is slightly more complex, but that complexity isn't relevant for the spill logic. So I decided to not add to the complexity of this session by also creating a completely realistic image of the hash table. So let's go with this simplified model of the hash table. So we keep adding data, and at one point we are out of rows in the build input, and indeed it all fits in memory. This is the happy scenario. There is no memory shortage. We are fine. Now, because the build input has been depleted, we open the probe input, we read a row, and now we compute the hash for this row. It's 4. Okay, that means that we need to search for matches, not in the entire rather messy image on the screen, which by the way is messy for us humans, but not as messy for computers, which are good at following pointer change. But chains is the English word, I'm sorry. English is hard, especially after midnight. But we only need to search in bucket 4. So SQL Server only has to compare this row to the 3 rows in bucket 4. It never sees the rest of the hash table. And then it will see are there matches or not, and depending on the join type, the correct input is returned. Then we read the next row from the probe input. This hashes to 7, and we only search bucket 7, which has only a single row. So you see that each of those searches goes pretty fast. So let's move it to the next level. A hybrid hash join is a join that actually starts as an in-memory hash join. So up to a point, it is the same. But let's move back in time a bit and let's pretend we're still in the build phase. So we have this data in memory, but there's more rows in the build input. So we read the next row and then we get very angry because memory is full. The row doesn't fit anymore. Imagine that there's actually no more space in the, I mean, if I could have wanted, I could have squeezed it in the animation, but imagine that memory is full. So we can't fit this row in memory anymore. That is when the in-memory hash join becomes a grace hash join. So the hybrid hash join is basically the term that says start as an in-memory hash join, but once you run out of memory, you realize, okay, I was too optimistic. I thought I could do it in memory. I can't. Now I'm going to degrade into a grace hash join. But Hugo, you now ask, you didn't tell us what a grace hash join is. Excellent question. That's the next slide. A grace hash join bases its idea on saying, okay, we have this hash table out of 9 or in reality thousands of buckets. Let's divide that hash table into a certain number of partitions. In my visualization, I chose 3 partitions. It will typically be a relatively low number, maybe 4 or 6 or 8 or 2. I don't know what number. This is not documented, so I don't know how many partitions SQL Server chooses. Um, 4 sounds quite likely because it's a nice multiple of 2, and computer people like multiples of 2. On the screen, I used 3 as easy visualization. On the screen, I also made each partition a set of 3 sequential buckets, which is also not realistic. The partitions are actually based on yet another hash function. So we have data, we hash that data to find the bucket number, but then we also hash the bucket number to find the partition number. In the visualization, I chose a simpler method, but imagine that this is also a hash result. So we have 3 partitions, each consisting of 3 buckets. At this point, we need to choose which, oh, not yet. At this point, we also need to access tempdb. Like I said, once we spill, we get data in tempdb. And what SQL Server does, assuming 3 partitions, SQL Server will create 4 files. Why 4? Because not 3 plus 1, 3 minus 1 times 2. The reason is one partition will remain, oops, that was the wrong click. One partition will remain active. 2 other partitions will become inactive. Those inactive partitions go to tempdb. So let's assume that we choose to keep partition 1 active. Then we need 2 files in tempdb for the build input of partition 2 and the build input of partition 3. But later we will also need files for the probe input of partition 2 and the probe input of partition 3. So that's why we get 4 files in total. We choose to keep partition 1 active. That means that buckets 1, 2, and 3 will simply remain in memory. The other buckets will have to be moved to tempdb. So we start with bucket 4. We simply read its data, and one by one, each of those rows will be moved from memory to the build file. And we probably, I hope that Microsoft stores the bucket number along with the data, because it would be a waste of resources to recompute it later. So let's just store it. Now we have already freed up some memory, and bucket 4 is now in build file 2 and no longer in memory. We can do the same for bucket 5, which is empty, and for bucket 6, which only has a single row, and all that data goes to build file 2. And then we also go through buckets 7, 8, and 9 to move that data to build file 3. And now we have plenty of room available in memory again to continue the processing of the data that we have. Again, partition 1 is active. I marked this in the animation by having that color slightly different from partitions 2 and 3. And the rest of the build phase can now continue to process. So we already had a row that didn't fit anymore. We can now compute which bucket it is in, bucket 4. Now bucket 4 is part of partition 2, which is inactive. So this data now is immediately added to build file 2. It doesn't go to memory anymore. The next row from the build file, from the build input, happens to hash to 1. That is part of the active partition, so this row still goes into memory. And we keep processing data that way, and once we are at the end of the build file, input, we have all the data from partition 1 in memory, all the data from partition 2 in build file 2, and all the data from partition 3 in build file 3. Cool so far? Then we go to the probe input, because we only now have processed all the build rows. Let's start with the probe input. And now the first row from the probe input hashes to bucket 4. Bucket 4 is not in memory. We can't search bucket 4, so this row also has to be temporarily set aside in probe file 2. That's why we need those probe files. If the next row happens to be for bucket 2, that is part of the active partition. This can simply be processed in the normal way, returning all the matching rows that we need to return. And then the next row may be processed, or maybe stored in probe 2, or maybe stored in probe 3, and we keep processing data from the probe file until from the probe input until the entire probe input has been processed. At that point, we have produced all the matches. We might need the final phase, but then after doing the final phase, we have produced all the correct results for data in partition 1. And we have stored all the data for partitions 2 and 3 distributed across the probe and build files. Since we have created all the results and returned all the results for partition 1, we don't need the data that we have in memory anymore. So we can clear it out, and now memory is completely empty, so we can make the next partition active. We choose partition 2, and at this point we can start reading data from partition 2 from the build file, and just copy it from the build file in memory in the hash table. We keep doing that for all the data in that build file until eventually it is all in memory. At this point, we have everything in memory from build 2, and then we can start reading data from probe 2, which is guaranteed to be part of the active partition. So this data we will always be able to process it in the usual way for each row from the probe input until we are done. And then once that is done, we can clear partition 2 again. We can clear the memory again because we're done with partition 2. We have all the results we needed, and we can repeat the process for partition 3. Put it all in memory, do the probe phase, and so on. The way I describe this, the Grace hash join as the next step in a hybrid hash join works this way. There's also a different variation that is called the full Grace hash join. According to documentation I read, SQL Server can do this, but very rarely. And basically, the full Grace hash join is SQL Server saying, you know what, I already expect that this will spill. So I started not using memory at all. I immediately create partitions. And if I now would create three partitions, it would be six files because all partitions start inactive. So we create partitions, we read the build input, we write everything to the correct build file. We read the probe input, we write everything to the correct probe file, and then we process everything. Why would we do that? Because it saves a bit of effort if you start in a hybrid version. You first stuff everything in memory, and then at one point you realize, oh, I need to put a part of that in tempdb. So that's an extra step as compared to instantly putting everything in tempdb. It is hardly ever used. Typically, SQL Server starts in the hybrid hash join. So hoping that everything will be okay with the in-memory hash join, degrading into the Grace hash join if needed. But it is important to note that this full Grace hash join also exists. Now, it can get worse. That's where the recursive hash join comes in. So let's move back in history a bit more. We are once more in the build phase. During the build phase, we started in memory, we ran out of memory, we created partitions because we degraded into the Grace hash join, we moved partitions 2 and 3 to the build files, we started processing more rows, partition 1 filled up again, build 2 and build 3 got more rows again, but rows just kept coming. They don't stop. So we get yet another row, and this row is for bucket 1, which is in partition 1, the active partition, but memory has filled up again. That's when we start to recursively do the same process. So partition 1 is apparently, even after being just a third of the total data, this partition is still too big to fit into memory. So what we do is split up partition 1 again. And because this is a simplified example with just 3 hash buckets left, you can't split very much, but there's at least a little bit we can split. I call them partition 1A and 1B. I'm pretty sure that Microsoft and SQL Server internally do not use that naming, but that is again to make it easier for us mere mortals to understand what's going on. So partition 1 is now split into 2 new partitions that each have part of the data. So now we have a total of 4 partitions. We only want 1 active at a time, so we have to have 3 inactive, which means we have to have 6 files. So we don't actually shrink files in tempdb. Those files in tempdb can just grow as much as you need. You can just add rows, there is no limit. It is my visualization where I need to make those rectangles a bit smaller so that I can create 2 more files, a probe file and a build file for partition 1b. 1b can be the inactive partition and 1a remains as the active partition. And now we can continue our process. The rest is the same as before. Of course, if we go on long enough, then this might repeat itself. Partition 1a might still be too large and we need to split it again. It's recursive. That's why this is called the recursive hash join. Now, there's a different type of recursive hash join, and I just moved back in time a bit again. So again, we are at the point where the in-memory hash join has already degraded into the Grace hash join. We added data to all the partitions, and even more data comes in, but memory doesn't fill up. A build file turns out to be way larger, and again, those build files have no size limit. It can just keep growing. Well, if your tempdb volume fills up, then you're out of luck. But let's assume that you have your data system set up correctly and that you don't run out of space in tempdb. So those build files can just keep growing. But SQL Server keeps track of the data that is in there. While writing to build file 2, SQL Server has some internal counters that it keeps to make sure that it knows how much data is in there. So we are now at the end of the build phase. We have processed all the rows. Partition 1 didn't overflow, it is still in memory. But SQL Server can at this point already see, oh, there's so much data in build file 2. Once I make that the active partition and try to load everything in memory, it will overflow. So at this point, SQL Server will already say, okay, I am going to split partition 2 in partitions 2A and 2B, as you see on the left side of the screen. Again, this means that we need more files. A build file 2B and a probe file 2B, and the build file 2 is now renamed to build file 2AB. And again, those names are my names to clarify what's going on. So why is it not built to A? Because SQL Server doesn't touch the data in there. We'll get back to that data later. But first, let's see the probe phase in action now. So we get data that is part of bucket 4. That is now not partition 2, but partition 2A. So it goes to the probe file for 2A. We get data for bucket 2, we can just process that data because that is the active partition. We get data for hash bucket 6. This is also partition 2, but it's now partition 2B. So this goes to probe 2B. And we keep processing data that way. So at the end of the probe phase, all the results for partition 1 are there. And all the data for probe 2A, 2B, and 3 is in the correct file. The build file 3 has the correct data, but there's something weird with partitions 2A and 2B because all their build data is still in a single file. Now we can free up the memory and make the next partition active, 2A. Where do we find the build data for file 2B, for partition 2A? In the build file that still has 2A and 2B combined. So we now start reading data from that build file, and every row goes either into memory, if it's bucket 4 or 5, or it goes from build file 2AB to build file 2B. We'll get back to that later. So at this point, we're basically sorting the data in build file 2AB into this is the part for 2A can go in memory, this is the part for 2B should go to the correct build file. And that's why we only now fill build file 2B. And we don't have a specific build file 2A. And that is how a recursive hash join works in the two cases. One, the recursion happens in the active partition, and two, the recursion happens in one of the non-active partitions, or one or more of the non-active partitions. So you can understand that there is a lot of reason to be angry. That's why all this is part of the anger phase. But once you are past that initial anger, it's wise to start bargaining, to start looking for solutions, looking for ways to make it better or make it hurt a bit less.
So
And
Hugo,
that's what,
sorry to cut you
yes,
off. There was a question during the anger phase.
that's okay.
And that was when SQL Server makes the hash value, is it taking the actual data itself and converting that into that hash value, or what's that process look like?
If you look in the execution plan in the properties of a hash match, and you have to look at the full properties, it's not in the pop-up. Um, or some well, part of it is and part of it isn't, but in the full properties you can always find it. There are two properties, hash keys build and hash keys probe. Those list the column or columns from the build input and from the probe input that are input to the hash function. And generally, well, always those are the join fields. So if you join sales order header to sales order detail on the sales order ID column, join blah to blah where on sales order a dot sales order sales order ID equals b dot sales order ID, then those two sales order ID columns will be the input for the hash function, and that will be decoded encoded in the execution plan by making that column the hash keys build or the hash keys probe. I think that answers the question, right?
Yes, thank you.
Good. So like I said, we start bargaining. We start trying to find ways to alleviate the pain a bit. So we have this dynamic destaging, but we can do some small things already. Once more, I'm moving back in time. I jump time a lot in this presentation, and I try to always indicate where in the process I am. So we are once more at the end of the build phase, but in this case, the data was a bit less. So we had the in-memory hash join as a start. We degraded into a Grace hash join, as you can see, because you see the partitions active, you see the files in tempdb. And at the end of the build phase, partition 1 didn't recurse. And you see that build 2 and build 3 are also pretty small. They didn't recurse either. In fact, they are so small that you could, in theory, add them together. That would be 7 rows, and 7 rows fits into our memory ground. So we created 3 partitions, but with hindsight, say, oh, we could have done 2 partitions. And that's exactly what SQL Server will do. So you now see on the left that instead of having 3 partitions, we have 2 partitions, partition 1 that we already had, and the new partition 2 plus 3. This also means that we don't need 2 probe files anymore. Instead, we have 1 file, probe 2 plus 3. But again, just as in the recursive process, we're not touching the data in the build file. We'll get there later. So now we can finish the probe phase as usual. Data for hash bucket 4 goes into probe 2 plus 3. Data for hash bucket 2 gets processed. Oops, that was 1 click too fast. Data 2 gets processed. I always forget where I have the animation to play automatically or where I need to click, so that sometimes happens. And then data for bucket 8 also goes in probe 2 and 3. In the previous situation, those would have gone into 2 different files. Now they go together in probe 2 plus 3. And we keep working like that, processing the results for partition 1, as always, storing all the other rows in that single probe file 2 and 3. We're done with partition 1, we can clear memory, and we can make partition 2 plus 3 active. The data for this partition is spread across 2 build files, so this is quite predictable what will happen now. Everything from build 2 will be copied into memory. And then we will also copy everything from build 3 into memory. Because at the end of reading the build input, we knew how much data is in those 2 files. There are no surprises here. We know that these 2 build files combined will still fit into memory, and then we can process data from the profile 2 plus 3 in the normal way. So this is the first part of bargaining where we make a slight advantage by eliminating 1 partition if it turns out that 2 or more build files can be combined into a larger partition that still fits in memory. The bigger the advantage is in dynamic role reversal. And dynamic role reversal also requires me to go back in time, but now to a different part. Now we go to a part where, yes, we did have the in-memory hash. We degraded into the Grace hash join. We created the 2 build files. We stored the build file for partition 1 in memory. In this slide that you see, there was no recursion, but the same dynamic role reversal can also happen after recursion. So I could have used a slide where recursion has happened. I chose not to. But now we're not at the end of the build phase. We also read the entire probe input. You can see that because the files probe 2 and probe 3 are already populated. And that is a sign that we processed the entire probe input. So that means that we also already returned results for partition 1. This is the point where dynamic role reversal can happen. So at this point in time, let's imagine that the data distribution was slightly different. We have a bit more data in build file 2 and a bit less data in probe file 2. Not so much that we would have to recurse and split partition 2, but you see that the data is slightly different. Like I said, partition 1 has already been processed. The results are returned to the client, so we can free up the memory and we can make partition 2 active. But remember, SQL Server keeps track of how much data it writes to every build file. It also keeps track of how much data it sorry, how much data it writes to every probe file. At this point, SQL Server knows that build file 2 is larger than probe file 2. And it is known that the hash match algorithm is more efficient with a small build input and a large probe input. We don't have that. So at this point, SQL Server says, I'm just going to reverse the roles of those two files. So the file that was previously known as build2 is now called probe2, and it will be used as probe input, and vice versa. Of course, that also requires that SQL Server has to internally switch if the join type is a left outer join to right outer join, or if the join type is a right semi-join to a left semi-join. It has to make that right-left switch in the join type. For an inner join, it doesn't matter. And it flips those two files around. And now it can load the smaller build input 2 in memory and then process the larger probe input 2, which originally was the build input 2. So, like I said, the algorithm is more efficient with a smaller build input. So for this partition 2, we now get more efficient processing. For partition 3, we don't apply dynamic role reversal because, as you see, in partition 3, the build file is actually the smaller file. Now, just when you thought things are going to be okay, there's this slide. Depression. We'll get to the worst of the worst in hash builds. Bailout. And again, we're going to travel back in history. So, as you see on the screen, this is a situation where we started in memory, we degraded into a Grace hash join, but if you see the partitions 1A and 1B and the extra build files, you will also see that there has been recursion. And because I start with only 9 hash buckets, I cannot do many levels of recursion. In reality, there would have been many levels of recursion before we reach this stage. But you see that we have data for just a single bucket. Partition 1A is now just one bucket. And we already have the memory area pretty full. So what if there's yet more data that also fits in bucket 1? Now, for something like this to happen, you need to have extremely skewed data where in reality thousands or millions of rows need to have the same value in the input columns to the hash function, or you need to be insanely unlucky with hash collisions. At this point, we realize we have another row that needs to go in partition 1A in bucket 1. It doesn't fit in memory. Okay, can we split it? No, partition is just one bucket. You can't split one bucket. So how are you going to fix this? It simply doesn't fit. Well, at this point, SQL Server says, okay, let's first assume that I just started with a full Grace hash join. So now I'm going to make partition 1A inactive. So I'm going to get to another case as well. As you see, this is case A, the single bucket partition in memory overflows. We'll get to the other case later. So at this point, SQL Server will say, you know what? Partition 1A doesn't fit in memory. I'm going to make that inactive as well and pretend that all of this was a full Grace hash join right from the start. So everything we have in memory is now in files. We keep adding data to those files until we have processed all the build input. No results to the customer, to the client yet. Everything from the build input is in memory. Now we open the probe input. Everything goes into the 4 files for the probe input. Nothing goes to the client. And we have now a stage where we have all the input in memory. And we need to process all this input. Okay, I'm going to pause this scenario. We're going to return to this scenario in a bit, because there's also the second scenario where a single bucket in a build file is too large. So here the situation would be, and this is similar to the situation we saw when I talked about um, recursive hash join, but now you will see that the data in build file 2 is almost completely for bucket 4. And I told you SQL Server keeps track of what it stores in those files. It doesn't keep data in memory, but it keeps counters in memory. And previously I talked about counters for the number of rows and the size of the rows, or the total size, but it actually has a counter for each bucket. So at this point, we have all the data for for the build input in memory. We have read the entire build phase. Partition 1 is okay. Partition 2 and 3 are in files. SQL Server sees, oh, I should split build file 2 recursive. And then it looks at the data and says, I have so many rows for a bucket 4 that even if I make bucket 4 a single bucket partition, it still won't fit. So we have the same basic scenario, but because it now happens to data in file and not in memory, SQL Server will at least continue with the rest of the process. So it still splits partition 2 into A for just bucket 4. We already know we'll run into problems with bucket 4, but we're still going to do it. And 2B for the rest. We're going to do the entire probe phase. So now we do return results. We get all the results for partition 1 to the calling operator, to the client, and we have all the rest in data. Same as I showed in the normal recursive process, except that we already know that we will run into a problem with partition 4. And I'm going to pause this scenario too and say we have now two scenarios. In one case, we have partial results returned and the rest of the data is in all the files with this weird split for build 2AB. And in the other scenario, we have no results and all the data in files. So we are at least in both cases in the stage, we have all the data in files and we know that there is at least one single bucket partition that is too large. And that's where we are now. The two different starting points, but we always end with a single bucket partition as a build file that is larger than memory. And we can't fit it in memory. Now, because we have everything in memory, we can still check for dynamic role reversal. Perhaps partition bucket 4 is like this in the hash, but like this in the probe. Let's switch them, problem solved. Good. That's why we do dynamic role reversal. We escape from the bailout scenario. But what if the build file is too large and the probe file is too large as well? The short answer is then we cannot do a hash join. So is this the point where Microsoft decided, you know what, let's just do a runtime error? No. Microsoft is very in the camp of, if we can return results, we will return results. No matter how much time it takes. And believe me, this is going to take time. So at this point, SQL Server has to realize I cannot do the hash match algorithm. And again, this only applies for that partition. All the other partitions can still be processed the normal way. There's only this single partition, or if you're very unlucky, it might be two partitions, but let's not go there. There is this single bucket partition where both the probe file and the build file doesn't fit in memory. So for this partition, we cannot do a hash match. The only alternatives to produce correct join results is to use the merge join algorithm or the nested loops algorithm. So let's look at the consequences of each. If we choose to say, okay, for this partition, we will do the merge join algorithm, I'm not going to go into a full description of the merge join, but the beauty of the merge join algorithm is that it's a single pass over both inputs, and like closing a zipper in your clothes, it all goes into each other, and very nicely you process you get the results. This requires the input to be sorted. The input to a hash match is not sorted, definitely not after stuffing something in memory, then taking it out again, and all the stuff we do. So we have an unsorted build input. It has to be sorted, so we need to sort it. Okay, we have sort algorithms in SQL Server, or we can sort it. Yeah, but remember that build file didn't fit in memory, right? Sorting happens in memory, and this build file doesn't fit in memory. So now the sorting of this build file will once more spill to tempdb. Hooray! I'm not going to talk about spilling of sorts, that's not the topic of today. It's slow, it uses tempdb, it sucks. And we have to do this if we want to do a merge join. Oh, and then that sorted data can't stay in memory, it doesn't even fit in memory, and we will need more memory later. So all those sorted results now go to a new work file or work table in tempdb. So even more I/O on tempdb. Okay, cool. We have the build file sorted. Yeah, but the profile has to be sorted as well. The profile didn't fit in memory either. So we get the same overhead yet another time for the probe file. And yeah, then we can do this efficient balanced line processing of the two sorted inputs. Hooray! Oh yeah, except that merge join has an efficient and a less efficient processing mode, depending on whether the data is one to many or many to many. And in a hash match, we never know the data, whether it's one to many or many to many. So we always have to assume many to many, which means more I/O to tempdb. Haha, I'm depressed. Perhaps merge join is not a good choice here. Let's look at nested loops instead. Must be better, right? So how does nested loops work? Well, we just read the first row from the build input. Doesn't need to be sorted, just whatever is in the first location. Good. Then we find matches in the probe input. Well, that's a file, it's not even a table, it's not indexed. So how do we find matches in the probe input? Read all the rows. Okay, fair enough. We read the entire probe input. We had to do that for the merge join as well as part of sorting, so that's cool. We can process that data and produce the output. But that's only the output for the first build row. After that, we go to the next row from the build input, and we read the entire probe input again. Now remember, this build file was more data than fitted into our memory grant, so it's probably a lot of rows. The probe file is also a large file because it didn't fit in memory. So we have this large file that we have to read entirely once for each row in this build file that, as I said, is a lot of rows. So yeah, we read this file, the probe file, the build file only once, but we read the probe file over and over and over and over and over again, and that is a lot of reads. So this is depressive as well. Yeah, I don't like this either. But we have to choose. There's no other way. We can do the merge join, we can do the nested loops join, or we can do a runtime error. But Microsoft said, no, we won't do a runtime error. They both suck. And SQL Server tries to pick the one that sucks the least, but it still sucks. So this is really where you get depressed, and rightfully so. But we have to accept our grief. We have to accept that we cannot always prevent spills from happening. They are a fact of life. And once you accept that, and once you accept that you have to deal with it, then you, and when I say you, I mean the engineers at Microsoft, can start doing some extra work to be smarter about this. And that's where bit factor filtering comes in. So as you see on the screen, we are once more at the end of the build input processing. We have stuffed everything for partition 1 in memory, everything for partitions 2 and 3 in the correct files because we were in a grace hash match. However, I lied a bit to you thus far, or rather, lying by omission. I didn't mention one little thing. In the hash table, SQL Server also tracks for each bucket whether it has rows or not. Now, for the first two buckets for partition 1, that is quite redundant because you can just see that there is a pointer. But during the writing of build file 2 and build file 3, SQL Server saw at least one row for bucket 4, bucket 5, bucket 7, and bucket 9. It never saw a row for bucket 6 and bucket 8. So in the form of a bitmap, this data is available to SQL Server. And why is that relevant? Well, because during the processing of the build phase, instead of saying this data goes to bucket 4, so profile 2, SQL Server will first check the bitmap. Okay, bitmap for bucket 4 is set. This data goes to profile 2. Again, as always, bucket 2 can be processed immediately. But now the next row is for bucket 8. SQL Server once more goes to the bitmap and says, hey, there is nothing in the build file for bucket 8. We have seen all rows from the build input. Nothing was for bucket 8. So I can store this data and then process it later, and then later I will realize there's no matches. Or I can say, hey, I already know that there will be no matches, so I will discard this row for an inner join or return it with some null values for a right outer join and so on. Depending on the join type, this row will now be processed as a non-matching row. We don't need to search the build input, the build files to see whether there's matches for bucket 8 because the bitmap already tells us there's nothing in bucket 8. So by definition, this data can be processed as non-matching data. The result is that at the end of the probe phase, we don't have all this data in the probe files. Some of the rows were never written. They were already processed as non-matching rows and not stored in the probe files, which means that those probe files are now smaller, which means that there's a higher chance that we can do dynamic role reversal, which means that there's a higher chance that we can avoid bailout. So by applying this bit vector filtering process, the dynamic role reversal process also becomes more effective. The bailout might be prevented in scenarios where it otherwise would have happened. And because right from the start we accepted our fate, we embraced that, yeah, spills might happen, we got back some performance. I still rather don't have a spill. I will always try to write my queries or to optimize and tune my queries to avoid spills. But this bit vector filtering may reduce the pain a bit. And that's the 5 stages of grief. Dynamic destaging, a hybrid hash join which starts in memory, degrades into grace hash, and then might recurse. Dynamic role reversal, bailout, and bit vector filtering. None of them are fun. Well, the in-memory hash join is, but this is the internals of a hash spill. At this point, I am done with what I had prepared, so are there any questions?
All right, chat, this is your opportunity to get any last second questions in, knowing that it is pretty late over on Hugo's side, so we won't want to keep them too much longer. Excellent job coming in from chat, and so far no questions. So it looks like,
Cool.
yeah, it
So
looks like
either I was completely clear or I have just melted 1,000 brains.
maybe a little of both.
That might also be the case. Well, for those who need to process this later, my email and my X handle are on the screen. So feel free to reach out to me if you have questions later. I will be happy to address them. And those who do have questions now, again, get typing. I am here now. You might get a live answer, which might also help with follow-up questions.
All right. So I'll give just another couple of moments for people if there are any last second questions for chat. Otherwise, I will remind everyone that our main meeting will be next Tuesday. We'll post the details soon on Meetup, meetup.com/trypass. And then our business intelligence and data science meeting, last one of the year. That one's already up. So check those out. And with no questions, I think we're going to call it a wrap. So thank you again, Hugo, for coming
Cool.
and speaking to us twice in 1 year. Much appreciated. Excellent presentation.
My
And
pleasure, and thanks for inviting me.
absolutely. And with that, we're going to wrap things up for tonight. So until we do see each other in a future TriPass meeting or wherever else, take care.